You can just solve something, write something out randomly and solve it on paper and feel, yeah, I got it right. Yeah. That's the nice part about simulation. Fill out the midpoint feedback if you haven't already. Um, I think most people have. And of course, ask questions. As I always say, please ask many, many questions. So that should be your.
Yeah, I can keep going. Can you give me co-host? Yeah. Okay. While he's doing that, let's just quickly go over nodal analysis because I think there's going to be some like correlations between how we solve nodal and how we solve the next topic of today, which is mesh. So just quickly, if you could just message me in chat privately this time, is how many nodes are here in this circuit? Just message me. Okay, I'm getting quite a few correct answers. Nice, nice. Okay. Okay. And I see a bunch of answers now. That's good. Okay. So you can go to the next slide. Yeah. So correct answer is the 3 nodes. I can see why you might think 5 because there's 5 kind of junctions. But when we're considering nodes, you have to remember that just because it's a branch, it doesn't mean that the voltage is different compared to another place on the circuit. And that's what we're primarily looking at. So as you can see here, we have one probably place with 0 voltage, our ground at the very bottom. I don't know if you can see. Yeah, nice. At the very top, you have one which is, we don't know the voltage is likely going to be the. Oh, sorry. Oh.
Uh, yeah. So how about the one which is in the battery, the most left part of the wire, which has V1? Would that be the same part of the node as in the most top of the circuit?
Yes, that is correct.
Yeah. Okay.
Yeah, that was good thinking. So the image is a little bit weird, but yeah.
And then how about the one to the very right, to the right of R3, that part of the wire?
That is also going to be a 0 because it's just a straight wire connecting them. And there's no kind of like branches between them. So you know for sure that it's
not from like the square node through resistor 3 and then from that?
No. So the square one at that junction of 4 resistors, that one's going to be distinct. And you can kind of tell because as you go across each resistor, there's going to be some voltage drop. So you know for sure that that's going to be a distinct node.
Okay.
Yeah. Okay. Any other questions about that? If you're still struggling with nodal, you can solve some of the problems that were in nodal with mesh. So hopefully mesh clicks with you better as it did for me. You can probably go to the next slide now. Yeah. What's important with nodal analysis, or I guess what's I think nice about nodal analysis, is some nodes are super easy. So you know immediately that's the node on the left. The nodes on the left are going to be 0 and 5 volts because the battery defines it that way. But that middle node, which is the node we'll use to actually solve the circuit, is what we don't know the voltage of. So nodal analysis, nodal analysis is about getting creative to find those harder voltages. And while some of this kind of skills will correlate with mesh analysis, the way we solve those problems is fundamentally different. So if you did struggle with nodal, it's fine. Yeah. Okay. So do you guys remember the 2 Kirchhoff rules from I think last week? Oh, yeah. Just like like a quick yes or no in the chat. Yeah. So I think it's what you call it Kirchhoff's current law and voltage law, right? I call it something different. I use like loop rule and junction rule, which is like decently similar. But what the idea is between those laws is that you know for sure, I guess with voltage law, that the voltage across any closed loop is 0, and for current law, that's current in to current out. So while we used Kirchhoff's current law to describe nodal, we're going to use Kirchhoff's voltage law now. And we're going to use that to solve questions. So yeah, here, perfect. So I guess exactly this is right. So rather than assigning voltages and nodes, we're instead going to find loops within our circuit, and we use those loops to solve for power, solve for current going through it. So yeah, perfect. So let's just get started here really quick. See on the diagram how there's two different loops, and we're going to call it loop 1 and loop 2. So I want you guys quickly message in chat what you guys think the total current is going through R3. When I mean total current, I mean, yeah, total current in terms of I1 and I2. Okay. That was a quick answer from Evan, and I guess everyone else is getting it right too. But yes, that is correct. Nice, nice. This is pretty simple. If you look at it, one current is going down, one current is going up. You have to subtract the two. This is going to go into superposition, which Ishaan will cover later. But the idea is that we are using the different currents of different loops. And then for the middle one, we're going to analyze it and say, okay, it's one minus the other. Sometimes it'll also be plus depending on how we define the circuit. So there you go, next slide. Yeah. Okay. This is a good basic example of a very simple mesh analysis question. So we want to look at the directions of the currents. In this case, I set it for you, but when you're solving it, you can set the directions either clockwise or counterclockwise. But let's just really just get into this question. We'll like hyperanalyze it. So first part, what is the voltage that the battery is supplying here? It should be a pretty easy one. Yeah, 5 volts, perfect. Yep. All right, now this is going to be tricky. What is the voltage drop of the next resistor here? You don't have to actually find the number, just find what it is in terms of I, because we'll solve for the number at the very end. Okay, nice. Okay, Evan got it. Yeah, so it's the voltage drop, remember from Ohm's law, is simply just the current going through the resistor times the resistor's resistance. So in this case, it's 2000 times whatever current. And in this case, we just wrote it as 2.
And just a quick note, you'll notice this circuit has resistances in KO, that's kilo ohms, that's thousands of ohms. But I'm just gonna write as if it's a regular number. And then all that's gonna change is that the final currents that we solve are gonna be in milliamps, as in 1,000ths of an amp.
Okay.
Yeah. That's just on a lot of circuit lab tests that you do in ScioVirtual in particular, they like to do things in terms of kilo ohms because that's more physically realistic.
Yeah,
but also there's a question, why is 5 volts for voltage supply? So we didn't draw where ground is. We didn't define our reference node of 0 volts yet, but in a circuit like this, it's pretty easy to just assign it to the bottom, and there's not really any other good choice of where to put ground. So we put ground at the very bottom of the circuit, and then if you trace that, I can't. If you trace that up through the battery, you gain 5 volts as you go through the battery. So right above the battery, to the left of that leftmost resistor, it's voltage of 5 volts.
Yeah.
Okay.
For mesh
That's all that
analysis,
is.
we're only considering the voltage added or dropped through each loop. So when the battery's adding 5 volts, so simply the voltage that the battery's supplying is 5, as it says there. Okay, and then finally, this one's going to be a little tricky, but based on the answer to the previous slide, you guys should be able to get it. Yeah, what is the voltage across the resistor? Voltage drop, sorry. Okay, yeah, some people are answering in chat. Yeah, okay. Nice. Yeah, remember the resistance for that one, we're just going to call it 1, and then the answers we get if for current will be a milliamp. So just 1 times current 1 minus current 2. All right, perfect. Okay, I'm just going to quickly pause here so you guys can just quickly see what we did. All we simply are doing right now to solve mesh analysis is we're just finding the voltage contributions in each loop. So for loop 1, we found the voltage added by the battery and the voltage drops from the resistors. Okay, and then here's where it's actually going to get interesting, because we know from Kirchhoff's voltage law that this must sum to zero, we can create an equation that lets us write our voltage drops in terms of currents. Okay. How do we know how much the middle one drops? Okay. This is a good question. And as I was showing earlier, the middle one drops is, perfect. Yeah. The current through it is the contribution from the current 1 and contribution from the current 2. In this case, they're going in opposite directions, so to subtract. In this case, we're not only looking at the left part, we're looking at the total.
Well, so okay. I think the confusion is, so we're going around that loop on the left to do Kirchhoff's voltage law, in that our goal is to write out the voltage drops of each element in that left loop and sum them up and set that equal to zero, because that's what Kirchhoff's voltage law says. But the actual currents going through each element are not only dependent on this loop. For example, that middle resistor, that middle resistor is touched by both of those loop currents. And so the voltage that resistor drops does depend on the current in the other loop. And that's why what we'll end up with is a system of equations, right? In general, any given element may have multiple loop currents or mesh currents going through it. We're just adding up the voltages within a single loop, but that doesn't mean that's the only current in the entire circuit.
To be more clear about that, when we're saying loop 1 and loop 2 has this current going through it, we don't necessarily mean that the entire loop only has that specific current going through it. We just mean that around the loop, particularly the areas where there's no other loops a part of it, it'll have that current. But in the case here with, let's call it the 1 kilo ohm resistor, there's multiple currents being involved there from each loop. So you have to consider both. I think that's a little bit confusing. Yeah, we don't just look at the current from the left loop. We have to look at the actual currents going through things. Okay, so let's go back to what I was saying before. Since we know from Kirchhoff's voltage law that all of these voltages must sum to zero, we can create a first part of a system of equations. Yes. Okay. The reason that this might be a little confusing is because end of the day, this is kind of like a model or a idealized way to look at circuits in which that we say that, okay, there's some current going through one loop and some current going through another. This is kind of like the basis of how we solve mesh analysis. So it might be a little confusing to make that jump. Like, okay, there's current going through loop 1 and current going through loop 2. But once Ishaan talks about superposition, it'll make more sense. But for now, I think you just gotta like,
what can make it a little more clear? Remember V equals IR, that's Ohm's law, right? So if I draw on the screen, is it possible to do from here? Okay, it's not. But if I have V equals IR, and I split that I into two different values, like I1 and I2, then it's just distributive property. V equals I1 plus I2 times R is V equals I1R plus I2R. The fact that Ohm's law is linear, I times R equals V, is what allows us to do that. Adding up these different loop currents is completely permissible because the voltage drops also add in the same fashion. Okay, so
that was a good way to explain it. Okay, so I think we've covered this. We can probably go to the next slide. Okay, now here's where we're going to use our first systems of equations, create a second equation, and then use both of them to solve. So loop 2, just want you guys quickly just in chat, like what's the voltage battery supply? We're going to go through this quicker. Okay. Yeah, 2 volts, perfect. Same reasoning.
No, wait, not quite. No, it's not 2 volts. Negative 2. Remember, we're going in the direction of the loop. Okay.
Okay, yeah, that was important.
And since our current is going into the battery here, we need to take that into account, because when we're going to construct our overall KVL expression, we need to make sure that we account for that opposite direction of the loop. We could have equivalently drawn this loop going in the going counterclockwise instead of clockwise, and then all the signs in the math that we've already done and that we will do would be swapped, and it'll work out the same. So it is a choice, and as you'll see in the next example, example 3, that choice can be made to be convenient for you.
Yeah. So I was saying, so it's 2 volts from the battery, but we have to consider the negative because since it's going the opposite direction. Remember that when you're going from positive to negative, then it's going to be a negative voltage contribution. So, okay. How much voltage does the middle resistor drop? Make sure you guys are keeping signs in track here. Yeah. Okay. There's a couple of people sending chat. Okay. Yeah. Okay, perfect. Yeah, I'm seeing answers in chat. That's good. Yeah, you can go next slide. Yeah, perfect. Yeah, in that case, it's I2 minus I1 times whatever resistance. And then the voltage drop does the right resistor. I think all of this should be pretty easy for you guys. Okay. Yeah, perfect. Yeah. Okay. Now let's create our system of equations let's create our second equation and then use that to solve systems. It is important to note signs here. Signs is really going to be the only tricky part of doing mesh analysis because you have to really keep track of whether voltage is being added or being subtracted from each component. Right? In this case, the battery's contribution is negative, but other than that, everything else should stay negative as well. So everything in this equation should have a negative sign on it.
Let's remember, we're talking voltage drops. Okay? A voltage drop is inherently a negative addition of voltage, right? It's taking away voltage.
Yeah.
So all of those numbers are positive. They are positive voltage drop.
Yeah, that's clarify. Okay. Okay, yeah, we're not going to actually solve the system of equations. Let's just use it on the tool. You'll always have, I think, a TI Inspire for Siley, so make sure you're using that and don't have to solve for the actual systems equations by hand once it gets trickier. Okay, yeah, so we have the answers for you. If you want to practice with the TI, you can do it later, but now I want you guys knowing these currents to actually find the numerical current going through that middle resistor. It's really quick in chat. Nice. Okay. Let me see. Yeah, nice. That's correct. Yeah. Nice. 1.75. Remember, you have to subtract 1 from 2 because they're going in opposite directions. In this case, one of them is negative. So when you're subtracting a negative number, you're just adding. Okay. Next slide. Okay. Now we have nodal analysis here. Is that still me?
I think it's my
Okay,
turn.
perfect.
Okay, so we're just gonna do the same circuit again, but with nodal analysis, so you guys can see how to do it 2 different ways. So first things first, identify the nodes, or in the chat, type out how many there are. 4 nodes, yeah. So we have one over here, one in the middle, and then it branches off here, one here, and then the ground is 0. And then we can write down the easy voltages at these nodes. So does everyone understand this step so far, why we have these voltages? Okay, yeah, because ground is 0, we have 5 volts from this, and then 2 volts from this source. And then we can now solve for the unknown voltage by writing the Kirchhoff's current law expression for that node. So we're just going through it kind of quickly because we've already gone through this in past lectures, but the missing thing is Vx. We have 5 over here, so to get the voltage through it's Vx minus 5 over 2 for a resistor, and then we do the same thing for each of these. So if you have any questions, just ask them, or if anyone's confused. Is everyone good with how we got to the equation? Yeah, go for it.
So basically, just for understanding, you're doing first, let's for the first part, Vx minus 5 divided by 2, you're doing the question mark thing, Vx, and then you're subtracting the voltage, and you're in the, what do you call it, the resistor value, and then you're adding all. And then you're adding all of the directions and that equals 0 because of the KCL, right?
Yeah, exactly. Because the current law essentially says that all the currents going out equals all the currents going in. And since there's no current going in, then all of them going out have to equal 0 as well.
Okay, thank you.
So again, if this is confusing to you, do problem set, I think B. It was the one that was released on Monday. There's so much practice with nodal, and even on today's problem set, will be released at some point today or tomorrow. there'll be even more practice with node. It's hard to just keep telling you the same things over and over again, and you really need to just work on it yourself and just process it yourself as you solve the problems. So, yeah. Don't use AI to solve these. That's not going to do you any service for your own learning. I mean, like you're not going to get. We don't care if you solve it or not, right?
Yeah,
So
like the homework doesn't
using
even have a
AI is not
solution.
gonna.
Like you just make sure you try and like solve it. Oh, I guess to study it. Yeah, I mean AI is a decent
Use
tool, but
use LT Spice. Just draw a random
yeah.
circuit, simulate it, and look at what happens. That's the beautifulness of LT Spice.
Yeah. So then after we get the equation, we just solve for Vx, which we're gonna do real quick. And then this is just like algebra. So if you don't understand it, then maybe refresh your algebra or come to office hours. But we get Vx equals 1.75 volts in the end. And we wanted the current through the 1K resistor, so we can easily solve for that once we know the voltage through the node. Because we just plug in Ohm's law, so I equals V over R to get 1.75 milliamps. Is everyone clear on that?
Milliamps? Or why not amps?
It's in milliamps because the resistors are in kilo ohms, but we just simplified it to be regular
Okay.
ohms. Yeah. Okay. Everyone good? I'm gonna assume we're good. Example 3, so nodal analysis was clearly easier there than mesh, but that's not always the case. So we can try this one, and we're gonna find the current going through resistor 2 below. So there's way too many nodes here, right? There's like, it's going to be really confusing if we try to find all the voltages through them. So we're just going to use mesh. And first we got to draw closed loops to cover all the components in the circuit. So these are our loops. Is anyone confused on like the loops?
Wait,
So
how do you know which way they should be going?
We have the arrows showing the way the current goes. So we just kind of like follow
Oh,
the
okay.
arrows.
Will they
but to,
always be there?
You you don't have
so
to set
yeah.
the current to go in any direction. You can pick either going clockwise or counterclockwise, and it doesn't change the map at all. You just have
Okay.
to remember that direction when you're doing your voltage drops.
Okay.
And the reason we draw those in this direction here is because those current sources already tell us what the current is there. And so since we already know what the current is, we might as well make our lives easy and have our pseudo currents, the mesh currents that we're putting in, be in the same direction. Because then we won't have to deal with negative numbers and all is good.
Yeah. Okay. Thank you.
So what is the current down resistor 2? Just type in the chat. Maybe you can't answer. Yeah, it should be I2 plus I3. I don't know why the answer says that.
Oh, that's
Um,
sad. That's my bad. Should be 2 plus 3. Sorry.
yeah. And it's 2 plus 3, not 2 minus 3, because you can see both these currents would be going down the resistor, and we're trying to find the current down the resistor. And in our last example, we had them going the same way, so the current was going down here and up here, which is why we subtracted them. Okay. But wait, each current source only touches one mesh current, which means this circuit is actually really easy because we already know the current flowing through all the meshes because it's only being supplied from one spot. Does everyone understand how that works?
No, what is the mesh current?
So a mesh current, basically, we're using it to sort of simplify how we solve the circuit. Okay.
Yeah, but like where's
So
it located? Is it like in the middle of the circuit?
So each one of those loops, I1, I2, and I3, that is an individual mesh current or a loop. So mesh current is a current that goes around a closed loop in a circuit,
Yeah,
right?
yeah. Yeah, yeah. But it
So
says current source only touches one mesh current.
yeah, so look at the top current source, I1 at the top of that circuit.
Yeah.
That current source is only touched by I1. Okay? So that means the current I1 just has to be equal to that current source. Okay, that's all it is. Because if there were two mesh currents on it, then it would be there's some or they're different that has to be equal to that current. But since there's only one, we know immediately what the mesh current there is. Same thing for I2 at the bottom left, right? Since I2, the current, the mesh current, is the only current that goes through the current source, and the current source forces the current to be 5 amps there, we know
Yeah.
I2, the mesh current is 5 amps.
Yeah, I get it. Thank you.
How I like to think about it when I was learning about mesh is that the mesh current is just the current that goes through the loop if nothing else was there. So for I guess for I1, if the bottom two boxes weren't there at all, the mesh current would just be I1.
Okay.
If that makes sense.
Yeah, it does.
Okay. And then just to find the current down the resistor, we add up I2 and I3. I think it's
Yeah, I can go ahead and take over and share. So now let's get a little philosophical for a second. Let's step back from the problems that we're solving and think about how we should be solving these problems. Okay. That last circuit that we just looked at was completely trivial with mesh. We had current sources. They immediately told us what each of the mesh currents were. And so we didn't need to do any thinking really. We just immediately knew the answer. And I can tell you right off the bat, current through R2 is 15 amps, I2 plus I3. Okay. But in general, if we see a current source or multiple current sources, mesh analysis is a promising method to use. Our goal is basically to save ourselves as much time doing math as we can, right? And so I have to go and solve a bunch of system of equations. I have to go do all this work. My life is hard. But with mesh analysis, sometimes I can get a much simpler thing. Okay. Or in this case of the previous circuit that we looked at, but this one, we only had one equation with nodal analysis. So you need to pick the right method depending on the circuit that you see. The current sources, yeah. So current sources are actually a voltage source. The actual architecture of a current source is a transistor current mirror that supplies voltage. We're going to talk about that next week, actually. But basically, a current source is a voltage source that can supply a variable amount of voltage at a fixed current. I know it's just a bunch of jibber jabber right now. It means nothing. But we'll talk about it next week, why it's because supplying current is not are there other circuits? Yes, and what a brilliant question you just asked, Jaden. So that's what we're going to talk about in a second. But so for these two circuits right here, on the circuit on the bottom left, do we think nodal or mesh would be better there? I kind of flashed the answer a couple times, but might as well still ask. Well, actually, it's nodal. The circuit on the left is definitely nodal. Okay, because we have a bunch of voltage sources, and so we know the voltage here already is 0 volts. We know the voltage here is whatever determined by this battery. We know the voltage here is determined by this battery. And so the only actual nodes we have to solve are right here and right here. Okay, our life is pretty easy. Whereas with mesh, we have this loop right here, this loop right here, we have this loop right here, and it's at least a system of 3 equations, if not more. Okay, so mesh is going to be difficult in this circuit. Is there a way? Yes, of course. So it depends on what you're solving for, right? If, say, maybe you wanted to find a node voltage right here, maybe you can do like an intermediate step and do some mesh. Remember that these methods are not anything unique. They're just based on KCL and KVL and Ohm's law, right? So there's nothing, as you can get creative, and that's good. That's what you should do. For the circuit on the right, it's hard to say. Probably nodal, right? Because we still have these voltage sources and we have a current right there. But mesh might also work too, right? And why I mentioned that is because even now when I do circuit analysis, it's pretty unclear whether nodal or mesh will be better. Okay. Nodal is always my first bet because I have less of a risk of messing up the signs when I do nodal. Okay. But really both methods are completely good. And whichever one you're more comfortable with is the one that you should use. Unless we have something like the previous one right here where it's just so clearly we should use mesh. I mean, look, we have all these current sources, they immediately tell us mesh currents. But there's also other methods of circuit analysis that we have in our toolbox. For example, we're going to talk on Friday about Thevenin and Norton circuits. We're going to talk just shortly about superposition. and even things like source transformation. Okay. And all these methods are still based on KCL and KVL and OLA. They're all based on the same principles that we've already learned. Okay. So yeah, guys, can we keep chat on topic perhaps? So just remember, whatever method we're using, it's nothing too special. It's still just the same principles that we've been using in any circuit analysis. So with that, let's talk about superposition, which if anything were to be special, why is there an asterisk on always? So if the circuit isn't planar, like if it's a circuit built in 3D that you can't use mesh analysis, sometimes you have like bridges and circuits and stuff. But like, we're not going to look at circuits like that. That's a stupid way of modeling circuits, like drawing circuits. That's only exactly. So Jaden is saying the right thing. Superposition does mean just add. And a lot of physicists and quantum enthusiasts like to talk about, oh, quantum superposition entanglement, but it's nothing special. It's just the addition of two states in the case of quantum mechanics, or in the case of circuit analysis, the addition of two currents or two voltages. Okay, there's nothing special about the word superposition. For anyone who does know physics, get it out of your head that superposition and entanglement are cool things. They're just very normal phenomena that make sense. Anyway, that was just a useless friend. So for the same reason that we can draw a circuit with loop currents and then add up the contributions from each of the loop currents, we can also solve circuits one source at a time. Okay. So this circuit right here, yes, we could use nodal since we can find that and do that. We could use mesh and we get the right answer. But let's use the method of superposition to try and solve the circuit. Because actually, when we're in the lab and you have multiple sources connected to a device, superposition is the most useful method we have because we can disconnect all the other sources and just keep one connected and then attach a different one and then a different one. And then just add them all up to see what does the resistor or whatever you're looking at actually behave like. So if you're doing circuit lab, odds are you're going to see something like this in a circuit lab that you do as a part of the event, right? So first of all, what we're trying to solve for here is the current going down through R2, okay? That's going to be this current right here. That's what we want to solve for, okay? So to solve for that, then what's the best time to use superposition? So in just general analysis, as we'll see, this is a little bit of a cumbersome method. It's not best, but it's very useful in the lab. But really, nodal and mesh, if you're just solving a circuit, are going to be what you use 99.9% of the time. So if we solve this circuit with only V1 and we just get rid of I1 and V2, okay? Then we solve it with only I1 and get rid of V1 and V2. And then we solve it with only V2 and get rid of I1 and V1. Then we just add up those contributions, and that's going to be the current through this resistor. The actual reason for this is deep, okay? It's actually not very obvious why that should work, but you can think of it basically how mesh analysis works. Each one of them is contributing a sort of mesh current that goes through R2, okay? But how do we isolate the sources? If I want to get rid of a current source or battery or voltage source, how do I get rid of it? I can't just remove it from the circuit. I have to take some consideration. So let's take a brief break from looking at the circuit on the right and look at the circuit at the bottom here, okay? We have a battery connected to a current source. So obviously this is a pretty useless circuit. You're just supplying power and then dissipating that power with a thing, right? It's not really doing anything. But let's notice, first of all, that battery can have any amount of current pumped through it. I can set that current source to 1,000 amps, and I can send 1,000 amps of current through the battery. That's fine. I'm going to be dissipating a lot of power. I'm going to start a fire probably, but I can do that. And in the same way, a current source can drop any amount of voltage. I can set the voltage of the battery to like 3,000 volts, and then that current source is going to drop those 3,000 volts, and that's fine. So the moral here, any current can go through a battery, and any voltage can drop across a current source. So if we want to remove a battery, we need to replace it with something that won't change the current, which is just an open wire. If I were to forget about the voltage drop and replace this battery with an open wire, the amount of current this current source supplies can still be the same, and we're all good, okay? And in the same way, if I were to remove a current source, we want to replace something that won't change the voltage. In other words, a break in the circuit. If I replace that current source with just a break in the circuit, there's going to be 2 points that have a voltage drop between them. How can an open wire keep current the same? It's the same reasoning that just if I have a series circuit, like if I have a battery and then a resistor, that the current around this loop is the same. Okay. If I just have a wire, then we're all good. Okay, we're not changing the current or anything. It'll be more clear how this works in a second, but bear with me. So first of all, let's start by trying to isolate the current source at the top. Okay, so the procedure to do that is we replace all voltage sources with short circuits, and we replace all current sources other than the one we're analyzing with a break in the circuit, open circuit. So you can see this battery right here is just replaced with a wire. Okay. This battery right here is also just replaced with an open wire. Okay. When you go back a slide, the slides will be sent out on Google Classroom, so don't worry about screenshotting. You'll have all the time in the world to take screenshots. So that's what we've done. We've short-circuited this battery, we've short-circuited this battery, and now we're left with just a circuit with one current source. So this now what we're left with is just a current source and some resistors, okay? And now we want to analyze this circuit to find, again, the current going down through resistor R2. But notice, there's a path of zero resistance right here, right? So any current that goes into there from the current source can go through this path of zero resistance and then come out here. If a current, you can think about the current as just like having a brain of its own, okay? And it has a choice. Am I going to go through the path that's resisting me, even resisting me a little bit? Or am I going to go through the path of zero? It's zero resistance because it's just a wire. A wire has zero resistance, okay? It has a very tiny bit, but for our purposes, the wire has zero resistance. So if the current can choose to go through the wire, which has zero resistance, it will. It's not going to go to a path that's resisting it. It's just going to go through the easy path where it's zero resistance. So in fact, no current even goes through here. It's like this part doesn't even exist. And current just flows around the outside, okay? This goes around this because that's a path of zero resistance right there. Okay, it gets short-circuited down the bottom. And so the contribution to the current through R2 is 0 amps. This current source I1 sends no current through the resistor R2. Okay. Now let's isolate the battery V1. Okay. So we want to keep this circuit, this battery, that's right there. But the current source, we need to replace with a break in the circuit. But for current sources, we literally just remove them and create an open circuit. This is called an open circuit. Okay. It's just completely broken. And you can see the battery we've replaced with just wire. It's a short circuit right there. Okay. So first of all, since this is a broken circuit, since there's no current that can jump. Current doesn't jump. Current needs to flow through a wire. So actually, it's like this top part doesn't even exist. Okay, because no current can flow through there, right? And so what we're left with is just this bottom part. And that bottom part's a very easy circuit to analyze. We know we can simplify resistors, we can use nodal, we can use mesh, whatever we want. We're not going to do that here. I'm just going to give you the answer. The current through the resistor going down in this smaller circuit is 0.12 amps. So the current that V1 sends through that resistor is 0.12 amps. V1 alone does that. Okay. And remember how we got to there. Let me just back up for a second. We first isolated that battery, right? We went from the circuit that had 3 sources to a circuit with 1 source by getting rid of the current source and just breaking the circuit and replacing the battery with short circuits. Then we realized this top part is nothing. It's a big nothing sandwich, okay? The only relevant place where things are happening, where current is flowing, is in this bottom part, the R1, R2, and R3. Nothing happens to R4. We found the current there. And now the last thing we need to do is isolate the second battery. I realize that it says V1 there and that the resistors are messed up. Just ignore the numbering of each element. So again, just to be completely clear, V1 has been replaced by a short circuit, and the current source has been replaced by a break in the circuit, okay? And now we have the same nothing sandwich that we had in the previous example. Nothing happens to resistor R4 at the top. We can just ignore that entirely. And now we're left with R3, R2, R1, and the battery. And we know how to analyze that. We know how to get the current through R2 in this circuit. We're not going to do it just for in the interest of time. We should know how to do that by now. If we don't, please ask on the classroom and I'll give a detailed explanation there. But in this circuit, the current going down through R2 is 0.15 amps. Okay, so now we've analyzed the circuit with I1, V1, and V2 individually. From I1, we get 0, okay? From V1, we get 0.12, 0.1. So, you know, I have a tablet, but I'm still drawing with my mouse pad. I don't know why. Okay. And then from V2, we get 0.15. Okay. And so we just have to add up those individual contributions and we get 0.27 amps flowing through R2. And that's, to me, it's a little miraculous that that works. I mean, it's still surprising, even though now I know like the deep reasons that this works. It does work, and that is a completely fine way of analyzing circuits. Now, obviously, if we were to analyze the circuit from the get-go with nodal, find the node voltage right there, find the node voltage right there. If we were to analyze with mesh, look at this loop, and this loop, yes, that works. But in the lab, it's harder to measure mesh currents. And so actually, the best method that we have available to us is superposition and then also Thevenin and Norton circuits, which we'll talk about next time. So those are really the methods that you use when you're working with circuits in the real world. Okay, can I re-explain superposition? Yes, of course. So basically, what we have a bunch of sources present in this circuit. Okay, each source does something to that resistor. Oh God, no, I don't want to look at Tesla. Stop, please stop. Okay, each source does something to this resistor. Why can I not draw? Okay, each source does something to that resistor. So voltage source V1 has an effect on it. Current source I1 has an effect on it. And current source, our voltage source V2 has an effect on it. We want to isolate those individual effects and just add them up together. That's all we're trying to do here. Okay. The consideration, the really key consideration that we need to make is how we isolate them. Okay. To isolate a battery, we keep the battery, but we replace all the other current sources with breaks in the circuit, open circuits, and we replace all the other voltage sources or batteries with short circuits. Okay. And then we just analyze it one source at a time. So that was what our first step was. First, we isolated the current source I1 by replacing V1 and V2 with short circuits. Found the current, 0 amps. Then we isolated voltage source V1 by replacing I1 with a break in the circuit and V2 with a short circuit. I always use the term, by the way, just as an aside, I always say break in the circuit because I think open circuit sounds like it would just be a wire. To me, I get confused by that term. So I'm very explicit. I say break in the circuit. But if you're reading something, a break in the circuit is the same thing as an open circuit. I just prefer to think of it as a break in the circuit because that's more physical to me. But anyways, we isolate V1 by replacing the current source with an open circuit or break in the circuit, and the other voltage source is short circuit. We find the current, 0.12 amps. We do it one more time, but now for V2, or the rightmost battery, we have 0.15 amps. Now, all we have to do is just add up each of those currents and we're done. We have our overall contribution, 0.27 amps, okay? So you could think if you have a circuit wired up on a breadboard or you've built a circuit, you know where your batteries are. And it's pretty easy to just disconnect the batteries and replace them with wires, right? And so this really is a technique that is useful in practice. And it's a fun theoretical exercise to work with and try to solve circuits with it. But the reality is you won't find yourself solving many circuits with this method. It's just something that's very useful if you need to work with a circuit in the lab. So yeah. Now here are morals for the day. Okay. Mesh and nodal analysis will get you everywhere in circuit analysis. This is the fact of the matter. Mesh and nodal are the most direct applications of Kirchhoff's laws, right? Kirchhoff's current law is used to get the currents going into and out of a node, and we use that with nodal analysis. Kirchhoff's voltage law tells us that the voltages around a loop add up to 0, and so we use that with a mesh current. And so by and large, you don't need anything else to solve circuits, at least on paper. But we can play a lot of tricks to make our life easier, to avoid having to solve systems of 20, 30 equations and reduce the amount of algebra that we have to do. The biggest trick is resistor simplification. So there's a bit of a review, but can someone tell me the equivalent resistance of the circuits on the left and right? Anyone? Yep. So the right is 20, the left is 4. Remember the rule, actually, I have to pull up the rule for, on here. I hope it's on here. Okay. Bro, it's not here. But the point is, you know the equations for parallel and series simplification. Okay, and you can look those up if you forgot it. But yeah. And superposition is another trick that we can play. And so if I want to remove a source from a circuit when I'm isolating a different source, what do I change to a short circuit? Do I change a voltage source to a short circuit or a current source to a short circuit? Yes, voltage. And so, of course, this is a voltage source. And the current source is what we change into a break in the circuit. Because remember, if I were to change a current source into a wire, that means a different amount of current could flow through there than what the current source says should flow through there. Okay, so that's not acceptable. And if I were to change a voltage source into a break in the circuit, that means there could be a different amount of voltage difference between these 2 points than what the battery says there should be. Okay, we're just trying to remove that source without impacting what else is going on in the circuit outside of this source. Okay. Okay. Voltage source at the top, current at the bottom. Circuit analysis is really all about playing tricks. Even drawing a circuit in general and using Kirchhoff's law, it's all tricks. Okay. We have a very simple set of rules. Ohm's law, V equals IR, KCL, what goes in must come out, and KVL, the amount of voltage you drop around the loop adds up to 0. But with that, we are able to do literally everything in circuit analysis. Okay. And so it's all about creativity and playing tricks in what you see on your paper. Okay. So that's your morals for the day. Go ahead, fill out the transform. I'm done a little early, so if anyone has any questions or wants an extra explanation of something, you to ask. I'm happy to elaborate. And again, please do attend. So here is the attendance form. That's attendance. And here is the midpoint feedback form. If you might have already filled it out for the midpoint feedback, but so yeah, if anyone has any questions, we'll stick around till time is up. And please do attend today's session at 9 p.m. Eastern on capacitors and inductors. I will be using LT Spice significantly during that. And it would be great if you had that on your computer. You don't need it because I'll just be showing it. But if you can play around with it yourself, you can always have some more fun with it. Attendance code is J5. Yeah, you're free to leave if you have no questions. Bye-bye.